हो गया क्या? Okay. Okay. Hello, good afternoon. Huh? Okay, so I think many of you might know me. The CS people might know me, but the others probably don't have not taught you. I just want to get a feel of, although I have the list of students, computer science undergraduates, can you raise your hand? So this is a computer science, okay. Electrical BTech, mechanical BTech, materials MEMS BTech, civil BTech, okay. MSc and MTechs, all departments, okay. And PhDs, PhDs non-CS PhD also. Okay, so there are few. Okay, all right. So welcome. So just to give you an idea, I've been teaching this course. I think some of you had emailed me. Come. I'll be teaching this for the 5th time. First 3 years, we just allowed computer science students. 2 years we just allowed computer. 3rd year I allowed selectively some engineering and math student. Last year I allowed everybody. So it was an experiment for me because CS students have taken computational intelligence, they've taken data structures, algorithms, optimization. Some of these components are used in different aspects of the class. So last year we were able to, manage happily. I think CS students also benefited based on the feedback. I got the highest feedback in my 10 years here in that class. It was 97% or something. So it means that all kinds of students benefited from this experiment because this is something which all of you, machine learning is the buzzword, no, in thing, what you say. So it's always good to have it on your CV in that sense. And also good because all disciplines are using machine learning. So in that sense, okay. So having said that, I'll go over a few of the modalities of the class, then we'll start the lectures. So what I do is, you'll get an email from me today, all of you. There are 223 students enrolled this time. So the classroom is really big, so we can't see that number, we can't feel it. But so there's large class, that's okay. I have taught bigger classes. You'll get an email from me today evening with whatever I'm talking today. So you see on the screen is a Google Drive. Everybody can read it at the back. So this is how I structure the things. The things which are important to you for the class are interaction, offline, and exam solutions. These are the 3 folders which you will be referring as we go along. But before I do that, I'll talk about few admin things which are here. So the administration thing first is, this time, although I've taught machine learning independently for the 4 years, this time Dr. Chandresh is helping me. So this is the split of the class. So what I am going to teach and what he is going to teach are in 2 different columns. So by the end of today's lecture, all these models will start making sense to you. So we have split it based on different kinds of models we'll work on. Geometric models, which are regression and support vector machines, and distance-based model, which includes a lot of clusterings. I think you guys who are sitting in the front row can sit more at the back so that, if you want, you can sit on the 2nd or 3rd row onwards. Are you okay? All right. Okay. So these three I will teach, although like I said earlier, I've taught the full course. This time he is helping me. And probabilistic model and logical models, which are decision tree and rule based models, Dr. Chandresh will teach. He is another faculty in the department. So we have split it equally. First 7 weeks I'll teach, last 7 weeks he'll teach. This is a week before the exam, so 7 weeks for that. Evaluation is equal 50%, although I am the course coordinator, which means that I'll make your final grade. And the good part is I'm a lenient grader, so you would, doesn't mean that everybody gets a double A. It doesn't mean that. There's 50%, 15% mandated, 1/5 of the class strength cannot get more than double A's, which means 15% of 200 would be what? 30, 10% will be 20, and then you add another 10 to it. 30 students approximately will get a double A. Then AB is, there's no mandate, so most of you get AB. Some who don't do work get BB. I rarely fail unless somebody's not done anything, but doesn't mean that you work towards a F grade. So that's one thing about the grading. So I'll do the curving, and Dr. Chandresh is relatively harsher grader, which is okay, which is his style. I am a lenient grader because I have a different philosophy in teaching. So in terms of TAs, we've written 4 TAs here. 2 of them are here, Kuldeep and Saurabh. But because there is a large class, we'll get a lot more TAs for it, which you'll come to know as we go along. In terms of the book, there is no book you should buy for studying the class, for studying for the class. But the textbook which we follow is Peter Flash, Machine Learning, Art of Science and of Algorithms That Make Sense. It's a long word. This is the book. But he'll hate me, the author, but don't buy it. They don't need to buy because I feel it's not a well-written book. It's a book we follow because it's a complete book in that sense. It covers all the topics, but it's slightly difficult to understand and some details are missing. So I also had a hard time to read this. So that's why I don't recommend to my students in buying such a book. But if you can get a hold of it, then that's okay. That's one. The other are reference books. So if you're a non-CS person, this term I'll use CS and non-CS often because just to differentiate between that some of you have the background and some of you don't have the background. Okay. So this is called Machine Learning for Absolute Beginners, although I never recommend these absolute beginners termed books, but this is surprisingly a well-written book. Every topic which we cover, it gives you a flavor of it with some examples. It's also not too expensive. If you can buy it, then buy it. This is a really good one for non-CS. CS people may have some idea. This book is, you see the one topic I wanted to highlight. Yeah. So this book is a very well written book. This is the second book in my list. Simon Hakin, Neural Networks and Learning Machines. Although the syllabus for this doesn't cover neural networks, as you would have seen. There's new neural networks here. The reason is that in the computational intelligence course which these computer science students have taken, neural networks has been covered in detail. So we don't go that direction in this book. But this book is good. It says neural networks and learning machine, but it has a lot of very good topics like regression is well explained. Support vector machine is very well explained with the all mathematics behind it. Principal component analysis. There are a lot of important topics this book caters, and it is a well written book. So if you have to buy some, even for the CS majors, if you have not heard about this book with Aruna ma'am, who typically teaches computational intelligence, then I would recommend you can buy this. The third book in the list is this Shai Shalav, and I think there's spelling mistake here probably. No, it's correct. Shai Shalav, Schwartz, Scheib and David. So this is also a very compact book. You can see it's not too thick. but it goes into the math behind a lot of models, which many times we are puzzled about. No, how come all of a sudden you pulled out a model out of thin air? So it doesn't happen that way. There is some math which goes behind it, and this guy tells that. But this is not the first book you should pick because it's slightly advanced. So in case you get a handle of these from the library, you can do it. But if you want to buy the first one for the non-CS and the second one for pretty much everybody. If you want to buy, these are not expensive books, 500-600 rupees. These are all Indian reprints. Okay. All right. So that's the overall layout of the class, which is in the split. Then student list, this is something not for you, but this is for us, what all students are enrolled. A little bit about my teaching style I usually tell, which I'll briefly go over, then we'll go over more of the material and then we'll go on the things. So my teaching philosophy, this is a few points. When I recently won the Teachers Award, the National Teacher Award, a lot of people are asking me what is the sealant, how do you teach large classes? So this is what I follow. So one important thing is I take all types of students with me, which means that there'll be slow learners, there'll be fast learners. And to take care of the fast learners, I give separate problems on the side. So I'll give you problems you work on by the time I make sure that everybody else comes on board. This is probably gifted to me. I'm able to break hard concepts into part. I emphasize goals at the start of the semester and revisit those. This is what we are doing for now. I put all the material on Google Drive, and everything which we do in the class will be recorded and put on YouTube as lectures, which doesn't mean that you don't come to class, but you come to class for fun, for the sake of learning. The learning happens most in the class in terms when you interact with me, when you ask questions. Probably I've not written here. If you're not asking questions, then I'm not teaching well. That is something my philosophy. If you're not asking questions, doesn't mean that the topic is hard or you didn't understand. It just means that I've not been able to get to your level, which is bad for me. So you have to ask questions, as many as you can. Stop me n number of times. However simple or trivial it may seem, please stop me. Because there will be one person who will take the courage to ask a question, and there will be 5 more who would have the same doubt. So it's always better to ask. Okay. Okay, because when I was a student, I also used to think, Pata nahi, this question looks too silly. But there's no silly question. There's always ask, basic thing. Periodic evaluations, of course, we don't have quizzes. Now come to evaluation. My goal is to make you learn. Learn in a happy way, or all this teaching philosophy which works in schools these days, we call it joyful learning. It's more about that you are enjoying the class and learning all along. But if you're not giving an exam, then which means this will not settle in your brain. This is now time tested by a lot of people and me myself. When you study for a quiz, when you study for a midsem, when you study for an exam, then only you are able to absorb, think, and these consolidate concepts. It's not a memory test. So of course, there are certain aspects you'll have to remember. Like if you don't know ABCD, you can't write a cat, right? So those basics you'll have to remember, but still when you prepare for it, then. So most of my lectures are also accompanied by a minor project, which means that now that you're coming from such diverse departments, everybody has their own problem. How you want to apply machine learning to this, I would like to see. For the masters and PhD, it's straightforward because you're already doing some sort of a research and you try to integrate the techniques from the class there. For the undergraduates, I usually share them list of papers, or I share them list of digital libraries where you search for the papers which interest you, the domain, and then you make a proposal around it, then you present it, and then so on and so forth, right? Okay, last thing is I rely on feedback, which by the time you would have known. I will, in the middle, 2-3 weeks down the line, I'll check how I'm doing. So you give me a feedback, so that is something. Okay, so that's about my class. So this was all administration. Now, how you would navigate the drive. So this interaction has 4 folders. One will be the lectures, which I'll keep posting before the class, before the start of this week. So this is the introduction and regression, which we'll do tomorrow. This was a feedback which I got multiple times, that I don't teach with slides. Most of the courses which I've taught, algorithms or optimization, even networks, compilers, data structures, all of them, numerical, all of them I have done on the board, because I feel slides, you tend to go faster and the students don't get it. But then when you have a bigger class, it's difficult. I can't write here. I can write on this, but it slows the things down. So we'll follow the slides, but I'll write on the white paper here and explain you the derivations. So whatever I scribble here will be uploaded also here. So recordings will be there, scribble will be there, but for your studying, the PDFs are good enough. In case you have a doubt, you can go back and see the scribble. You can rerun the recording. So that's the second thing. C is the recording. So of course there will be a YouTube playlist created for my lab, which is the Math of Data Science lab. We'll put the link here. Then finally, tutorial lab. So this first tutorial. So by the way, the lectures for this are Monday, Tuesday, 1:30 to 2:30. On the timetable, there is a slot of Wednesday, 2:30. But that's an extra slot. That is something which we don't need. This class is 2020, which means that this is 2 lectures and 2 hours of lab. So usually it is 2 hours of lectures and 1 hour of tutorial, and there is a separate lab for that. But here the lab and the lectures are combined. So we'll have Monday, Tuesday lectures 1:30, 2:30. Wednesday we'll keep it as a free slot because it's more interactions than we need. In case there's a holiday, Monday, Tuesday, or Wednesday I'll keep for another reason, I'll tell you. And then Thursday, 4:30 to 6:30 is your lab, which will be lab/tutorial, which means that you'll switch between the two. Tutorials are where you work on a analytical problem, and lab would be where you code that particular model up and test it. So that is what we'll do. So this first lab on Thursday is just on Python. You may be using, I'm sure programming, everybody is comfortable, right? Because you do first year programming, at least the undergraduates do. You do it in C, C++. Sorry? C++, okay. So Python, because Python has become the language in AI these days. So it's good idea to learn it. It's not too hard to learn. So this first lab we're keeping for that. There are some resources in it. Yeah, so there are tutorial links which we have added. Make it slightly more bigger. Then there are books, there are video links. So I'll say that get comfortable with it, get it out of the way early on. It doesn't mean that these 2 hours will be enough for this. You'll have to go home and practice on it. Even the masters and PhDs, if you are, even if you're not a CS major, learn Python. It's a good asset to have, always. Okay. All right. So that's about the interaction part. Then what I have also created a folder, second folder called offline. So what offline does is it augments your learning besides what I'm doing an in-class instruction or a lab instruction. So there is supporting material. So as we go along, I'll keep uploading supporting material. The very first I've done is an old tutorial on artificial neural networks. So this is for those who have no idea about neural networks. You can go ahead and read this. The CS people already know, so they can skip it. But I'll upload a lot of material here, which means that if you're missing a background in optimization, which these guys have taken, the 3rd year computer science had taken last year with me, which will be a foundation of support vector machine, we'll upload it here. What is a Hessian, what is a gradient, what is constraint optimization. That brings me to the question of Those who are missing the background, I'll take special lectures on Wednesdays. So Wednesdays, we'll keep it for the non-CS people for the missing background. Not this Wednesday because we've just started regression. But next week when we come to support vector machine where the very first foundation of optimization is needed, I'll take a lecture on that. So the CS people cannot come, the CS undergraduates. CS masters, PhD should come because I don't know where you have studied this, in which college. So we'll keep Wednesdays for that. Alright, so that's the supporting material. Then what happens is you learn in the class, you do some tutorial, but you want to practice at home. Of course, the internet is full of problems to work on, but we have selected certain problems from each of the topics and we'll keep uploading them with solution here in the practice section. So that is where you would do. This will probably start next week onwards. And the last thing is the homework. So what are homeworks? Typically I follow the US pattern because I am trained there. The courses there are very intense in terms of every week, besides you have to submit a homework and there is a plagiarism pledge you take that you have not copied or something from this. But in India this doesn't work. You guys copy from each other, hands down. So I stopped doing it after 1 or 2 years. I said it's a lot of pain. You can't fire the whole 60 people class. No? In the US that would happen. There have been instances where students have been kicked out of the program because they copied the code. So, there was a code as part of the homework and there was a plagiarism pledge. When you compared it, it was 80% similar and they were fired. So fired in the sense kicked out. It's not a job. But in India, it doesn't work. So we don't per se grade the homeworks. But whatever things which I'll teach in the class, there'll be certain parts which I'll leave for you to work out. So you go home. Going home and studying on it is always a good thing. And if you're enjoying it, it's complementing your research, you like your research, then it should not feel like a course. It should feel like a fun learning experience, something like solving a puzzle or a riddle. So those homeworks will be here. Okay, so finally the last thing, exam solution. So as soon as you give a quiz, I'll upload the quiz with the solution. You give the midsem, I upload midsem with the solution. Of course, I'm not going to give you the endsem. That will be only on Chandrash's part. So the way he will run the course is different. This is only for my part. So I don't know how he runs his courses. So that you'll come to know when he comes. Okay. So that's all about the modalities. So now let's start machine learning. Any doubts? All good? Happy? Abhi tak happy? Okay, good. I also crack a joke in the class usually to wake those who have taken courses with me, to wake you up. To wake you up or to make the mood a little lighter. When it gets too mathematical and you start getting sleepy, or this is after lunch, so you will feel sleepy. That I know. And my way of speaking is also a little sing-song. I put you to sleep. So to break that, I have to use more of inflection. Wake up, something like this. Okay, so let's start. So today is just an introduction to get you a flavor of it. Tomorrow we'll do regression. There is 3 lectures on regression. Then there are 5 lectures on support vector machines. Then there are 4 lectures on distance-based models. So this is how we have split it. Okay. So this is a little copyright which I've been copying it from the Corona days. This is when I started making slides because I was not making. Okay, so which copyright means that don't post it on the internet. And the reason is not that I am doing something too path breaking there. The reason is that there are figures in this which have been taken from the books and resources which are copyrighted, which means that you can use them, but you can't publicly put that is yours. So I don't want to get into trouble in saying that I took somebody else's copyrighted content and posted it on the internet. So that's the reason we say don't post it. But you can download it, keep it with you. Okay. So let's start. What is machine learning? We'll see what are the types of models which you just saw in the syllabus: geometric models, probabilistic model, logical models. And then there are types of learning which we do. All right, so what is ML? Okay, so what is machine learning? So the name says itself, machine and learning. So you're programming machines, in this case computers, to optimize or use past behavior. So what do? Learning is used, sorry, yeah. So learning is used when human expertise, for example, doesn't exist. Humans are unable to explain, solutions change in time, solutions are adapted. This is just verbose, but this slide is more informative in that. So I'll tell you an example for this. So for example, you have to predict, for example, rain. So we want to build a weather model and we have to predict. You have most of you have these apps, weather apps, and you've got it's showing this much humidity, this much this, and the chances of rain are 20% to 80%, and so on and so forth. So this is all models which are doing work for you. But typically, if machine learning was not there, let's say 20 years back, 10 years back, or AI has been there for 30, 40 years, but even beyond that, what did people do? The physicists used to do the work, all the work. They used to create these analytical models. They used to say, we're going to take this humidity and, how much of air quality is there, how much dust is there, all these things and we're going to create some sort of an equation out of it. Typically, equations which we remember are in terms of differential equations, which you study in your first year or second year. Partial differential equations or an ordinary differential equation, you have an input, you have few state variables, you have an output. So you make a model out of it. Dy by dx is equal to x plus y square plus e to the power something. How did they reach those models? They spent hours, weeks or years even trying to figure out what models will work. Or these mechanical engineers, all of those who are there, they know there is a fluid model, you use the Navier-Stokes equations. There is a solid model, you want to use some other Poisson's equation or something, right? All these equations, how did they came? These were not mechanical engineers who made it. These were all the physicists who spent hours trying to replicate a phenomena and come up with an equation, right? So that is why the pace of science discovery at that point of time was slow. When machine learning came, it says that it's going to be a black box, that's what it's like, learning in example based on empirical mathematical model instead of analytical ones. So there's no equation for it. There's a box which will be some sort of a model, which I'll tell you what a model is. You train it with some data, you keep training, and then you keep predicting, right? So like your brain, the best example of a model is our brain, that when we are very small, nobody knows any language. You live with your parents and your brain learns that language, that you learn Hindi or you learn English or whatever, your native language. It gets trained with it. And then when it's trained, it starts predicting, it starts forming its own sentences. So there is a whole model or an equation formed inside the brain which is producing those results. So that is what machine learning is. So it says deals with program that can learn from data. The program creates a model based on training examples which allows it to generalize and make predictions about unseen data. So that's the nutshell. All right. Important points to remember. So important points to remember is there are 3 parts to it, which I'm going to highlight in the next slide. Machine learning is concerned with the right features to build the right models to achieve the right tasks. So if the example I was using was weather prediction or rain prediction, that is my task. What is my features? Features is the quality of air, the humidity in the air, or the wind speed, or how much clouds is there, what kind of clouds are there, how much is the cloud cover, do you have mountains in the vicinity where it will hit and give a torrential rain? You don't know. So those are all features input to your model. The point is to predict the rain, and there would be some model which will process all of this and give you the answer. So that is the 3 things which is given on the next slide. So it says features, models and tasks. So task is very clear. We'll talk about all of this more detail with another example, not just the climate example. Models, I've not told you, we'll come to those. but features are workhorse, which means that how you pick a particular feature, the humidity is very important, and that's why they call the workhorse of the machine. Focus of this class for my instruction is not on the first or the last one. The focus is only on models, which means that I'm going to tell you all different types of models which are there, which means the black box, what goes inside the black box, how to build these models, and what is the math behind it, how did people come up with those models. How to use it would be for a particular problem. So if you are a material scientist, you want to predict that deep earth materials, how much strain or stress they can bear, that is your task. And then the features will again come from your MEMS faculty trying to say these are the material properties we need to study. So all that will be put together into the model to answer your question. Make sense? Okay, so that is what machine learning is. This figure, I think, is taken from this Gartner book. It looks a little complicated, but I'll just go over it. This is data acquisition. A big part of machine learning is also data acquisition, which means that because you have to train the system, right? So there's a training involved, so the data is important. So you get from enterprise resource database, mainframes, IoT devices, you process them in batches. Once you have the data, you do feature engineering. All this will be more clear when you do your project features, that you get features from different things, like you're studying plant height, and you're for example studying the thickness of the tree, for example. So those will be in different scales, and you want to use all of that as an input to tell how much your plant will grow, or how much fruits it will produce. So all that has to be normalized together. So this is where you transform data, you normalize data, you clean and you process. This is what we are studying in the class. We are studying machine learning models, and then you execute it and you deploy it. Okay, how to solve a task. So although I gave you an example, another example which I give you more from the computer science point of view is something which we face every day. You get an email and, for example, you applied for a job, and your employer says that we'll send emails, so make sure you mark our email address as safe, in the safe list. So which means that there's a probability that email from that unknown person could go into your spam folder. The antonym of spam is called ham, which is not a spam, HAM, that's the word which we use. So what would you do? For example, a lot of spam emails which we get is about lottery. You won this much lottery, which used to happen actually 10 years back. Abhi to kuch bhi spam aa jati. So there's spam for almost everything. Earlier it used to be lottery, you won this much $1 million. So how would you train your email system to identify a spam is that you will use this contains the word lottery. Remember that it has to be marked as a spam. The next time when you get an email which says some sort of a variation of that, which means says you are the winner, which means that it will now probably figure out that, okay, lottery and winner are together related, so this will also be marked as spam. So those are the things which the system will do. So you will take the object, there will be features you will extract, you will train them with certain part of that, and then you will start predicting with real data which is coming along. A lot of these days we get emails about, for example, I get is about conferences. There's so many conferences, you don't know which one is good, which one is not. So often they go into the spam folder, because there are very few tiny little set which are really good. Rest of them is just to make money or something like this. So most of them go into. So now whenever a conference related mail comes, it goes in the spam folder. So I have to always check that maybe this is a important where I actually submitted a paper. I'll have to check the spam folder. Is that okay? So that's the overall bigger picture of machine learning. I've not told you about the black box, which we'll start from tomorrow, but this is what it does. Okay, now coming to the heart of the work, the types of models. So like I said, which you probably saw in the in the class split also, this is what we are talking about here now. So we are talking about geometric models, which are regression model and support vector machines. So these are typically you do linear, so these are called linear model, distance model. There's probabilistic model, then there's a decision and rule based model. Okay, so we are in the representation part. So by now you would know, you don't know what these means, but intuition for geometric model is that you're using some sort of a distance measure or some sort of a geometry to figure out something. The something will be clear in a minute. So you could use hyperplanes, you could go to linear transformation, you can use Euclidean distance to figure out. So these are all geometric model. Probabilistic model, again, now coming to background. So those who don't have probabilistic background, probability background, you would need to know a little more of probability. So although these two parts are falling under Chandresh's thing, if he is not able to cover this, I'll come and teach you a little bit about probability on that Wednesday after the break. So don't worry about it. I talked with Chandresh that I've been teaching this and I want to allow everybody to, like I've done in the past. So he's okay with it, which means that he understands there will be students who don't have the background. So then finally there's logical models. Logical models are the easiest example to tell is like a decision tree. You make a node and you decide which side to go, then you go more side to go. So the background for this is minimal, but these are very simple models, but they are powerful because they are more transparent. If you look at the other models which we've seen before, the geometric model, you don't sometimes know how the data is being segregated, classified clusters. But in trees, you would have a transparency of data, bringing to the concept of, which is a buzzword of explainability, the explainable AI, which we call. So these models are inherently explainable, whether it's a rule-based models or it's a tree-based model and so forth, so forth. So these are models. Now to tell how well your model is working, you need a metric. Does everybody agree? You're given 100 emails, out of which, you have to classify them as spam or ham, and you're able to correctly classify, or maybe out of which maybe 30% emails were spam, but 30 emails were spam, but your system was only able to correctly predict 20. Which means that there'll be certain accuracy which you'll have to check how well your model is working. But there's a problem with accuracy. Can somebody tell me? Using accuracy as a metric to tell how well your model is working. Anybody? This is so far, I can't see faces clearly also. Maybe you guys cannot sit in that and sit, there's a lot of space here, come and sit here, at least I could see the face and identify, although I'll not be able to remember. So the problem with accuracy is, you would need to know the correct answer to tell how your accurate model is. Like I said, no, there were 100 emails, out of which 30 emails were known to be spam, and your model only predicted 20 emails correctly as spam, and the remaining 10 it thought was ham, they were correct. So the ratio of that will be 20 divided by 30. So that's the percentage accuracy it's trying to tell, right? Everybody agrees? But at this stage, I know that there were 30 spam. How did I know? Because I manually went through the emails and figured it out. This was important, this was not important. But in real life, that will not happen. For the training the system, yes. If you trained with your system with 100 emails, you'll be fine. But let's say 1,000 more emails come. You'll not manually go over each of them. That defeats the purpose of building a machine learning model, correct? So accuracy is good, but you can't always compute accuracy of your model. So there are n number of ways to check how your model works. And these are all listed here. I'm not explaining you these because they will be specific for a particular model. Whether what kind of model you're using, there will be a particular metric to tell how well it is working. Finally, there's another component of the model which is called the optimizer. So when you make a model, typically you try to formulate it as a minimization problem or something, and you find a minima of something. So to do that, you need to do some sort of an optimization, whether you're doing a combinatorial optimization, which is, you know, often NP complete problems. You're doing convex optimization, which you know there is a global minimum, or you're doing general constraint optimization. So this part, the CS people are aware. So those who are not aware, we'll do it on the Wednesday, like I said. Okay, now the third component. So if you recall, the very first thing which we talked about was, you know what is ML, you know the types of model, you don't know what they mean, but you know the names of them. Then there is how would you train your model. You have a model, you have to train it. Everybody agrees, you have to train it for it to be able to predict it, something. Huh? So there are different types of learnings which you do. So there is called the supervised learning. These guys would know, CS people, and who do competitive programming even would know. Supervised learning, unsupervised learning, reinforcement based learning. So what is supervised learning? So there is an example here, and there is an example regression and clustering which form in unsupervised. But I'll start with this supervised learning example, which I give from one of my, well, this is a common problem. If you're doing healthcare, machine learning for healthcare, one of the big problem here is to classify a particular image which you are there, whether it is a good image or does it have a cancer or not. So cancer diagnosis using machine learning is a supervised learning technique. For example, you're looking at breast cancer images. You know that these are, you know, normal, abnormal, or benign, or malignant, something like this. So you would first take those and classify them. So for example, this is the tumor size and this is the age. So if the tumor size is small and the age is less, then you'll say these are good, you're training them. But if the tumor size is large and you're older, then it means that it is it is a malignant tumor, there is a cancer here. So you will take all these images, put them into the model, which will separate it. Now you can do many models to separate it. Here they've done it with just a hyperplane, just a line in a two-dimensional. In an n-dimensional, it's an hyperplane depending on the dimensions of your problem. And in this case, we typically use a support vector machine, which will be clear, and you've classified it. Now, when a new data point comes, it will try to see which side of the hyperplane it lies on. If it lies below the hyperplane, then you'll say it is benign, but if it lies on the other side, you'll say it's malignant. So this is called supervised learning. Why? Because you already had data to tell you and build this hyperplane. You have a supervision here. There was a labeled data involved of the two classes, the benign class and the malignant class, right? So this is called supervised learning. Another type of learning which is common is the unsupervised learning. Now what is unsupervised? Where you don't know which class your data belongs to. This typically happens in clustering problem. This is typically a classification problem where I talked about machine learning in healthcare. This is a clustering problem where, for example, you've got every living organism. This example I'm taking it is from plant studies, machine learning for plant studies. Let's say every living organism has a whole genome associated with it, even humans like we do, which is series of ATGC characters, which, you know, you've gone through the corona phase, you know, the sequencing happens. Whenever a new variant mutation comes, you sequence it. What do? You take this ATGC characters, which is infinitely long, and keep generating, which carries the properties of that particular type of species. So now that, let's say you're given, in this example which I talk about, is a soybean plant, and you're given 100 species and you've gotten 100 whole genome sequences. Now you want to tell, out of these 100 species, which are drought resistant, which are insect resistant, which are flooding resistant. You don't know. You know that out of this 100, one I know is drought resistant because I've physically grown this plant in my lab, and I know this one is drought resistant, this one is, you know, insect resistant, or this particular insect, but I don't know about the others. So what I'll do, I'll take this whole genome sequence and cluster them. So now, depending on how many clusters you form, that also is an open question, which is a hyperparameters on how many clusters you form. Let's say you're only forming 3 clusters, drought resistant, insect resistant, and flooding resistant. And now when you'll be able to group them using some model, then you can tell, okay, this plant I knew was insect resistant, so all the others in the vicinity of it will be good too. So this is how you predict. So, but there's no end label for all of them. One of them you may have to be able to cluster them and figure out the inference out of it. Okay, so that's unsupervised learning, that you discover patterns in unlabeled data and so on and so forth. Okay, so yeah, so now I think that is all I have for today. So this is about the data sets. As I said, data is of utmost importance in machine learning. You pick the wrong data set and you are screwed. You know, you have to find data for your problem, but sometimes papers don't provide. Nowadays, the trend in machine learning is whenever you publish a result, upload the data with it so that people can use. UCI, University of California, Irvine is leader in that. They keep creating this data. Where do you look for papers? This will be more useful when we come to your minor project. So those are very prestigious journal, Journal of Machine Learning Research, IEEE Transactional Neural Networks, Pattern Analysis and Intelligence. So those are the three I usually refer. This machine learning is Springer Journal, where we recently are submitting something. In the computer science domain, I know you come from all different domains. In computer science, conferences are important. Only 1% of the 100 conferences which you hear about are actually good. But these are the best of all. So International Conference on Machine Learning, International Joint Conference on AI, NeurIPS, ACM KDD. These are the places where you should go and see what recent work is being done. And acceptance rate in these vary from 10% to 25% range. I mean, these are sometimes more prestigious than even journals which I just mentioned above. But the good part is that these are rapid dissemination of information. So in case you are very interested what is being done in machine learning for materials research, go to ICML. So ICML is the conference to look for such things, and you'll get an idea for that. Okay. Yeah, I think that's it. Any questions? You didn't ask any questions, so I assume you didn't learn anything. But there was not too much to ask. But from tomorrow onwards, please ask questions. Huh? Any other doubt? All good? Did I make you sleep? You awake? Okay. All right. Thank you.